but I will get started as people trickle in. So it is my great pleasure to introduce Professor Strachan from Purdue University, where he's the Riley Professor of Materials Engineering. He got his bachelor and PhD from the University of Buenos Aires, then did a postdoc at Caltech, and then spent some time at Los Alamos, I think.
Yeah.
And Professor Strachan is an expert in a whole lot of things. I know him mostly as one of the first leading kind of reactive simulation people, energetic materials and polymer fracture. But now he's got a whole host of interesting AI and uncertainty quantification areas. And it's really inspirational stuff. So with that.
All right. Well, thank you. Thanks for coming. Thanks. Yeah. Thanks for the invitation. It's been a great day, and it's going to continue to be a great day. It's good to see old friends and make new friends and meet new students. So this has been very exciting visit. So I'm a recovering physicist. Okay, so let me take you back almost a century to this very famous paper by Paul Dirac, where he said that we basically know all the fundamental laws to describe chemistry and biology. And he didn't mention material science because that wasn't a field, but all of material science. But then he warned us that solving these equations was very hard, and that it was important and desirable to find approximate practical ways of solving these equations, okay? And this is why many of us are here, okay? The fact that these equations are hard to solve is why lots of the people sitting in the room have jobs today. And this is very inspirational even today, right? With tools that even someone like Paul Dirac couldn't have dreamt at the beginning of the 1900s. So of course he was referring to this. Let me okay the recording so I can get that out of the way. He was referring to the Schrödinger equation. That's Schrödinger. If you combine that with StatMech, you can basically predict chemistry, material science. This is Boltzmann. This is Gibbs, okay, the first American superstar scientist. Now, the problem is solving these equations brute force. We've been talking about this. Trying to solve that brute force would take the age of the universe in the fastest supercomputer we have today. And so people like Walter Kohn develop approximate ways to solve this equation in minutes on a laptop, okay? So advice to students, if you take a problem that takes the age of the universe to be solved, and you make it in a way that it can be solved in minutes, you win a Nobel Prize, okay? So there's your advice for career advice. So in the 50s, a little bit, more or less at the same time, Dorothy Alder wrote the first molecular dynamics code and published the first molecular dynamics paper. This is when you do F equals ma and you solve how atoms move, and there's some interatomic interaction. And in those days, that was revolution. Okay, people didn't think you could actually do that and predict anything meaningful. So it's really took a lot of thought and leadership to do that. He was at Livermore. A bunch of people at Los Alamos, also in the 50s, developed and published the first Monte Carlo simulation. So this is Nick Metropolis, which we now call it the Metropolis Monte Carlo algorithm. The person who actually wrote the code that was used in the paper was Ariana Rosenblatt. So Ariana and her husband, the Rosenblatts, and Ed Teller and Augusta Teller were the other co-authors. Okay, and I think it's interesting. Ed Teller, if you watch Oppenheimer, he was there. He's the neutron bomb guy. There are two female colleagues, okay, two female co-authors, not colleagues, which was rare in those days. Okay, people used to not include those. And also interesting note, Ariana Rosenblatt died of COVID a few years back, okay, in San Diego. So this was in the 50s. In the 80s, you could argue that that was the birth of computational material science. Okay, these type of tools were mostly in physics and in chemistry, But in the 80s, we had the ability to make more quantitative predictions, birth of computational material science. And we'll talk a little bit about what happens next, okay? And I think a lot of you, the young folks in the audience, that's up to you, where we take these field and this journey. So in my group, we follow Paul Dirac's advice, okay? And we use approximate versions to solve the Schrödinger equation, different approximations to look at how materials work and operate and their properties at atomic scales, okay? From mechanics at extreme conditions to electronics and transport to polymers. And I'll give you a few examples, okay, of the type of work that we do. Of course, we live on this earth, and so we do AI and ML. And I'll tell you what I think are the opportunities and the interesting things that we've been doing on ML. And at the same time, we operate this infrastructure called NanoHub that tries to make simulation and data pervasive, globally pervasive, okay, so that everyone actually benefits from these tools. Okay, so that's the plan for the next 3 hours. So I joined the field in the early 2000s, okay? And in those days, for the first time, we had the ability to do molecular dynamics with reactive force fields that could break bonds and form bonds. And so we decided to look at mechanochemistry. So we decided to take this molecular crystal called RDX, it's an energetic material, and smash it into itself and create a shock. So we would put mechanical energy into the system. That shock heats up the system and compresses the system, and eventually it leads to chemical reactions, okay? What we saw out of this first ever dynamical simulation of mechanochemistry at extreme conditions is that bonds were breaking super fast, right at the shock front. And the understanding back then was, well, the shock comes in, it puts a lot of energy, all of these degrees of freedom thermalize. It's a process called up pumping. Dana Glott from here, chemistry, did a lot of work there. And then the system thermalizes to some temperature, and then there's thermal decomposition. Okay, I can use regular rates at high temperatures for the decomposition. What we saw is very different, just bonds being broken mechanically. So fast forward 1 decade or so, I was at Purdue. My students working at Los Alamos were able to run, going from these 32 molecules to 9 million atoms, okay? Every atom does whatever it wants, F equals ma, completely reactive, every hydrogen, everything is there. This is an actual real shock wave running through the system. When the shock interacts with a defect, it generates what's called a hotspot. It localizes the energy of the shock spatially, in a small space that gets very hot. And this hot region, the hotspot, reacts faster than the rest. And if the hotspot is hot enough and large enough, it turns into a deflagration wave, okay? And this was the first ever simulation of a shock to deflagration transition in an energetic material with atomistic detail, okay? So for as long as we could run this simulation, this deflagration wave kept going. This is very important because this is a key step in the initiation of a detonation. So we want to understand how explosives initiate for safety, for transport, right? Your airbags in your car are explosively driven. And so we need to understand very well when things will go off and when things will not go off. So developing this predictive understanding is very important. This was a key step to doing that. Just like the first ever, these simulations early on, what we found is that this hotspot that was generated dynamically by a shock wave was way more reactive than what we could anticipate based on its temperature and its pressure. So if I take a system and I compress it and I heat this up to the same temperature, it doesn't react nearly as fast. So this is path-dependent chemistry. It's not just the thermodynamic state, it's how you got there, okay? This was a very puzzling result. It was so puzzling that trying to explain this result was one of the main reasons why we put together a team and we worked on a MURI project funded by the ONR, by the Office of Naval Research. And the idea was can I go from electrons, atoms, all the way to a microstructure of an energetic material and understand the initiation of reactions, how sensitive material is, how safe they are. And of course, you can't do just this computationally. So our team had experiments at matching at each of these scales. So at every scale, we could do an experiment and compare and try to understand and validate the individual models around them. So the goal was to, and these are MURI projects, multidisciplinary university research initiatives, okay? They're very nice projects, very fundamental research. And we were trying to answer this question. And I think we did. So I'll tell you a little bit what we learned, okay? Why are these dynamical hotspots so much more reactive than an equivalent hotspot? So this is a shock just like before, okay, from our center. And we create a hotspot. This is the temperature field, okay? The color is temperature, right? It expands, it recompresses, that's super hot. And so we look at this, and this is a non-reactive simulation. This hotspot wasn't big enough to react, so it dissipates. The temperature dissipates. And for years, we've known about hotspots. Now, hotspots are localized energy. You can localize energy as temperature, which is basically kinetic energy at these high temperatures. But you can also localize it as potential energy. And what we found is that in these dynamical hotspots, there's more energy localized as potential energy, so molecular distortions, latent potential energy, than what it is localized as temperatures. So temperature doesn't tell you half of the story of the hotspot. What we found is that the potential energy is more intense. These are the same units of energy. It's more intense and it's more permanent. It doesn't dissipate nearly as fast as temperature. You can diffuse away this internal strain in the molecules. So if you zoom in, what happens is these molecules, this is a molecular crystal, that they like to be flat. At the hotspot, they're all twisted out of shape. They're literally bent out of shape, okay? And so that was the first hint that the reactivity may have to do not with temperature, but with the potential energy, okay, with the distortions of the molecules. So we ask ourselves, is this important? Is the fact that these molecules are twisted out of shape important for kinetics? And the answer is yes. Or this latent potential energy accelerates the reaction, so you can be at the same temperature, but a highly distorted mode. This is not a weird, extremely hard to understand concept, right? You're starting from a higher potential energy state, so you're going to react faster. Your reagent is excited. And so it does affect the kinetics. That's what we were trying to explain, but it also affects the chemical reactions. And so the way you decompose as a molecule, which bond breaks first and what proton transfer occurs first, is actually affected by this molecular strain, okay? So this is mechanochemistry. And of course, we didn't invent mechanochemistry. Mechanochemistry is known. And I'll show you an example, right? So if you take a molecule, you pull from it, you break it. This is and we can understand that by having an external force. It basically changes the energy landscape that your reaction lives around. This is an example of a mechanophore. So we're pulling on this molecule and we're going to break this spiral bond. and these molecules change color when they break the bond, okay? So this is the type of mechanochemistry that people have characterized. It's two-body elongation type mechanochemistry. But if you remember our molecules, we're not elongating, this is a shock. So it's many body distortions that add to the latent space. So we developed a technique in the simulation technique where we can go into, this is the mechanophore, this is the energetic material, and go there and apply external four-body forces and distort the molecule, and then look at the effect on chemical kinetics and decomposition time, okay? So, and we showed that the adding this external potential, instead of pulling, elongation, distorting, has an effect on the activation energy. It has an effect on the chemical kinetics that matches what we see in these gigantic dynamical simulations around the hotspot, okay? And again, we call that many-body mechanochemistry. I think this is an effect in polymers. It's very important. If you imagine condensed phases, you really almost never have elongation, but your molecules are going to be distorted, strained in many body manners. All right, let me continue with the story, but take it a little further. These simulations that I was showing, I had a single hotspot, okay? And if you looked at the hotspot, it was a cylindrical hotspot. We shock, it creates this nice, the void, we had a cylindrical void that generated a nice crescent-shaped hotspot that reacted, okay? And my human brain can understand a spherical void. You know, I'm a recovering physicist, you know, things are cylinders or voids. In reality, that's not what happens. These materials look much more complex. And so these materials are plastic bonded molecular crystals. So each of these cyan color, that's a molecular crystal, and has a polymer binder, and you have this polycrystal composite. That's what the real materials look like. And if you take one of these materials and shock it, this is a 30 million atom simulation, you create not one hotspot, you create a family of hotspots and a distribution of temperature that originate not just from one pore, but lots of little pores, pores that are oriented, have different shapes, they're oriented at different directions. You have heating based on interfacial heating. There's lots of mechanisms all operating at the same time. And I can understand one hotspot. I cannot predict, look at this structure and tell you this in any quantitative manner. So we looked for the ability to map microstructure to properties, to field properties using machine learning, okay? And so we took our simulations, we ran a bunch of these simulations, different microstructures, and we use a technique called convolutional deep neural networks to try to learn the mapping between the initial microstructure, 3D microstructure, 3D image to the final 3D temperature field, okay? And I'm not going to go into the details, so I can cover a lot of cases, a lot of examples, and you can ask me. But what these guys do is they have convolutional layers. So the convolutional layer looks at in this particular case, a 3 by 3 by 3 matrix of the initial image and extracts features. And then you have pooling, and pooling, what it does is it takes a group of these and picks salient features. And it just keeps the salient feature. As you pull, you get a smaller and smaller image from where you bring information from further out and further out. So if you have a void and it's close to another interface, with this pooling mechanism, you learn that that's the microstructure, okay? Convolution and pooling. And then we train it with the input being the initial microstructure. I'm going to tell you what the channels are, and the temperature, hotspot temperature. That's what we want to do. So let me show you an example of a configuration that was not used for training, okay? So this is a configuration that's never been seen by the model. And our three descriptors for the initial microstructure are total density, the density of the molecular crystal, and the product of the density between the crystal and the polymer, because that highlights interfaces. And so you can see some interesting features from the initial microstructure. There's a big void here. There's a void, elongated void here. There's another elongated void here, but it's at an angle, okay? And there's an interface here that you can see highlighted. And so this is what the MD result shows, and this is what the model predicts, okay? You can see it's almost identical, okay? It predicts where the hottest void is going to be. It predicts this other hotspot that's important. This guy that's oriented, it's there. It's a little weaker because it's not aligned with the shock direction, so it becomes a little weaker. This interface, there's no pore there, no significant pore, it lights up. And we did a lot of testing of the ability of the network to predict pores that it hasn't seen, and the performance is truly remarkable, okay? With a speed up, that's 10 to the 8, the computational cost. After training, 10 to the 8 speed up compared to the molecular dynamics simulation. I'm not going to show you results, but we've been training models that are multimodal. We combine information from molecular dynamics and coarse grain simulations. And the coarse grain simulations are cheaper, but they're not as accurate, okay? And you can actually train these models, and when you give data that's multimodal, you have an input that says, this is MD, this is coarse grain, cheaper version. And the model learns to tell the difference. So you can train with data that's not all super expensive, and you can have the benefit of getting an answer at the expensive level, okay? The other important thing to say is, you probably know that for AI, you need a lot of data, and you do. This doesn't mean in this particular case that I need 1,000 simulations. We could get away with about a dozen simulations because one simulation has a lot of information. One simulation samples all sorts of local environments, different voids, interfaces. So from one 3D map, you learn a whole lot, okay? We were surprised by this, but it's actually very powerful. And we're using these type of models. They're so fast that we're plugging them in continuum simulations so that the model can predict subgrid information, and we can then take this MD simulation to millimeter and many micron scales. Does that make sense? And the model tells you what happens under the resolution of the continuum level simulation. All right, let me switch gears. I'm going to switch gears 2 times, and I'm going to tell you a little bit about the work we're doing in polymers, and I know many of you are interested in polymers. And the example I'm going to show you is how we make carbon fibers, okay? So carbon fibers that are used, as you know, to lightweight anything from aircraft to cars and bikes, competitive bikes. You start with a polymer called PAN, polyacrylic nitrile, and the first thing you do is you spin it. And when you spin PAN, what you do is you kind of align the chains, okay, of the polymer. So the chains become stretched, and so you have a multi-phase polymer with amorphous regions where the chains are all twisted and more ordered regions. And then you go through a process called oxidation and stabilization, where you make it react to create these cycles, these ladder type structures that you see over there that can withstand the high temperatures that you need for the last step, which is carbonization. Okay, so then you take these ladder structures, you make this into these graphitic sheets, and that's what a carbon fiber looks like. So if you look at a carbon fiber in a cross section, you have a lot of these graphitic sheets all bent almost like if you take a newspaper and you roll it, okay? So the sheets are all bent, you have hairpin defects, all sorts of things. That microstructure determines the properties of the fiber. Okay, so we would like to understand how we go from here to there, right? And what are the steps? And 50% of the cost of a fiber today, as you know, they're very expensive. That's why they're mostly in high-end cars. Comes from the processing, very high temperature, very costly process. So when we started, these pictures were the best we had in terms of a molecular level understanding of the process. No actual molecular model. So what we did is starting from the polymer, spun fiber, stabilized fiber, trying to create physics-based molecular models for each of these processes, okay? And I'm going to give you a little bit of a flavor for what we learned. First thing, and this is a very puzzling observation. You can probably all tell me the answer why this is puzzling. So I told you when you spin the fibers, okay, the spun fiber, what you start with is critical for the actual performance, okay? So understanding that structure is very important. You have, when you spin it, you have ordered regions where the chains are more or less aligned, and you also have an amorphous region, which is like a regular amorphous polymer. And experimentally, both calorimetry and mechanically, there's two glass transitions, okay? And the high glass transition, the high glass transition is known to be associated with the amorphous region. And then the ordered region has a lower glass transition temperature, okay? And if you know the glass transition, if you know what it means is you have a rubbery material, high relaxation time, and you go through the glass transition temperature, basically freezes in place, right? That means you became a glass. You would expect the order region to have a higher glass transition temperature, not a lower glass transition temperature than the amorphous. It's more order, it's lower in energy, it's more stable. And so this was very puzzling and no one knew why. And so we decided to do some simulations, okay? So we built amorphous pan with many papers, lots of experience doing these type of simulations. You heat it up, you equilibrate it at high temperature, you cool it down, and you see this change in slope. That's the glass transition temperature. If you compare that value with the experiment, you need to be about 30 degrees higher than the experiment because our cooling rates are 10 orders of magnitude faster than experiments, okay? So if you ever see an MD simulation and they predict the glass transition temperature right on, they're wrong. You have to be higher because you're doing 10 orders of magnitude faster cooling. All right, so we understand that very well. When we do the crystal is higher density. It's now going to have a lower glass transition temperature. No way. Does that make sense? So that's what the simulation showed. That's what everyone expected. And so the answer, I'm going to cut to the chase. We took a system, very large, and we actually, in the computer, spun it. We took the biggest polymer that we could afford to run, and we stretched it to 11 times its original length. So in the computer, we have ordered regions and amorphous regions in the same simulation. Gigantic strain, and what you see is that all of these ordered regions are surrounded by these nanovoids, okay? Because that's where the chains align, right? It's not very surprising that when you align more strain, those are going to be surrounded by these nanoscale regions, nanovoids. And so now when you look at the relaxation dynamics of these stretched heterogeneous system where you have both the ordered region and the amorphous region here behaves just like this guy, just like our amorphous region. But the ordered region behaves nothing like the perfect ordered model that we have, because these nanovoids speed up, accelerate the mobility. So even though they're ordered, they're very fast relaxation. They have a very low glass transition temperature. So if you look at the relaxation dynamics, these structures match this peak, okay? So we think it's that nanoporosity that explains the fact that the ordered region has lower glass transition temperature than the amorphous region. All right, last thing, there's two steps of chemical reactions when we go from a stretched spun fiber to a carbon fiber. The first one is the creation of these ladder structures, and the second one is graphitization. Those timescales, I showed you a lot of reactive MD simulations for the energetic materials. Those reactions, they're extreme conditions. They occur in 100 picosecond timescales. So those are things I can simulate. These guys, these chemical reactions occur on timescales that are seconds. So I cannot simulate them. And so what we did is we combined molecular dynamics with a Monte Carlo approach to, based on the local geometry, decide which atoms, which reactions are going to occur. So we do molecular dynamics, the polymer reacts, and then if you're close, not just two body, but many body criterion, we form the bond. We force you to connect, okay? And we accelerate the chemistry that way. So you're going to see the birth of this. This is a single chain, and you're going to see here how this ladder structure is forming. Does that make sense? This is isolating a single chain in the system, and this is the full simulation. So now I have this stabilized structure, and now I can do the process of carbonization. This is in a different paper. What you see here is sticking out. These are the ladder structures coming towards us. So this is a cross-section of what's going to be the carbon fiber. And we do the same thing, and we start going through graphitization, carbonization, and we create the cross-sectional picture of the carbon fiber, okay? If you remember the picture I showed you before, the cross-sectional area, we see the same features, we see the same defects, we see the same, our simulations predict the right transverse modulus. So we believe we have at each level of the steps of the processing models that can actually capture what's going on those structures. And this is important because in this case, I cannot build from scratch a molecular structure of a stabilized carbon fiber because I don't know what it is. It's very complex. The only way to do it is going through the process of making it, okay? All right, so I mentioned how AI can help with physics-based simulations. I'm going to give you one more example of machine learning to help us make decisions, okay? So we have a project from NSF to design new metallic alloys using machine learning. And the approach we use is a very general approach called active learning, okay? That is it's an optimization approach that's an iterative approach and builds on machine learning. So you start with existing data, okay, from the literature, from your lab, from whatever. You create a model, whatever your favorite model is, that can predict the output that you're interested in maximizing or minimizing your quantity of interest. And then you use that model to predict the expected outcome for all the possible experiments you could run next. And based on the predicted mean and the predicted uncertainty, you select, the model selects the next experiment that you're going to run. Does that make sense? And then you run the experiment or the simulation, and either you're done, you found the golden material that you're after, or you plug in, you add your data to your data set, you retrain your model and iterate. Okay, this is called active learning because you hone in, you generate data that you need in the conditions that are of interest. either because you don't know much about a certain parameter space or it's a good performer, okay? And so we did this to discover high entropy alloys with, our goal is to have a good combination of high temperature strength and low oxidation resistance, where there's nothing there today, okay? Empty space of property. And so let me show you how it works. We start with existing data. We use Gaussian process to model the existing data that we have. Gaussian processes are very good because they have a natural way of capturing uncertainties, which is very important to make decisions. And then, and this is important, we delegate the decision-making process to the machine learning, okay? The professor is not telling you what experiment to do next. The model is telling you what to do next, okay? In this case, we can process alloys in batches of 5. So we tweak the model predicts 5. We go to the lab. This is not autonomous, okay? It's an actual student that takes clues from the model, cues from the model, and runs the experiments, okay? And so these are the results, batch per batch. And in about 6 batches, about 23 experiments or so, we found the highest, the aluminum-containing high-entropy alloy, that's the hardest, okay? Hardest aluminum-containing complex concentrated alloy in very few experiments. Our design space at the beginning, that's also important, was 65,000 alloys. We use CalFAT calculations, thermodynamic calculations to narrow that down to 5,000. That was very important. So it's not just AI, domain expertise, what you are learning about material science or chemistry or whatever your field is critical. This is not just out of the box and they run. But it really accelerates your decision making, and you're really also delegating the decision making to the machine. All right, so the last few minutes, I want to tell you a bit about what we're doing on NanoHub and with some other interesting AI results, with the goal of making these tools and the data pervasive. So we can use them in education, we can use them in research by people who are not computational geeks like myself and my students and many of you sitting here. How can we share this? So we run this infrastructure for open simulation and data. We have served 250,000 simulation users, okay? These are not visitors. These are people who come to NanoHub and run simulations on NanoHub hardware. This is cloud computing, completely open. We have more than 1 million visitors every year and lots of contributors, okay? And I hope after today, we're gonna have a few more contributors and you can all go there and publish your own work and share your work and your data. So what do we have? What we offer? 800 simulation tools that look like apps. Okay, so this is a molecular dynamics simulation. With 2 buttons, you decide, I want to run this type of simulation. This is the temperature, click a button, and it runs it for you. So we use it in undergraduate classes to teach students about mechanical properties and dislocations and resolve shear stress, okay? Without having to learn, be a computational geek. And we have a lot of AI stuff too. This is something that it's very interesting. So we have users in 95% of all R1 institutions in the US. So R1 are PhD granting high research institutions. We're in 65 of all technical minority serving institutions and in 43 of all technical institutions in the country. So we have better presence in minority serving institutions than in regular technical institutions across the country. Some of our bigger users, UIUC, by the way, is at the top. I could show you the list. Near the top is Purdue. The UIUC is probably 3rd. But then we have Ball State and R2 University in Muncie, Indiana, in the top 10, okay, with MIT and Harvard. All right, I think it's very cool. So what do? This is the input file for the type of simulations that we do. It's called LAMPS. If you do quantum espresso, your input file will look different, but equally strange, okay? This is a made-up language. And in order to run ND, you have to speak LAMPS, right? You have to be able to write this. And that doesn't mean that you know molecular dynamics. It just means that you speak LAMPS. That's all it means. And so on NanoHub, we wrap this around to do specific jobs, and with a few clicks of a button, you want to say, I want to do a crack simulation or a tensile test. You can run the simulation, click a button, it runs on a supercomputer, the results are displayed back to you on your web browser. So as the user, you have to do nothing. All you have to know is what is molecular dynamics and what's happening. So this has allowed us to make this research-grade code something that can be used in undergraduate education, okay? And you can do that for research or for education. All of you or many of you have codes that you could share or expertise that you have to set up a simulation that might be interesting to others. You can do that on NanoHub and publish it. I'm going to tell you more about that. Now, these GUIs are very exciting, okay? But now, with LLMs, it's just a very different way of communicating, okay? And I believe LLMs are going to become universal interpreters between human researchers and the underlying research infrastructure. So this is a tool that exists on NanoHub. You can go to NanoHub and say, I want to run a simulation for aluminum using this potential. I want to do melting of aluminum. You write in English. And GPT-4 actually generates that stupid input that we were talking about. GPT-4 actually speaks LAMPS, so you don't have to. And so on the tool, you can then click a button and we run it. Take that structure, that input file, you can tweak it if you need to tweak it. And we run it, we store the results in a database that's discoverable, and you can actually type and write to GPT, plot this versus that, okay? So I think we're not far from being able to write a paper where you write the method section of the paper, you describe what you're plotting versus what you're plotting, and you get an actual figure that you can put in a paper, okay? This is a relatively simple simulation. We actually wrote a paper on this. We marked over about 50 types of different inputs, how accurate they were, whether they run out of the box, whether they needed modification, how much work they needed. And you can read the paper, but the bottom line is, depending on the complexity of your prompt, it can run out of the box if it's very simple, or it might need modification. If it needs modification, probably that's 90% of your work, okay? We did the same thing for quantum espresso in my class. I taught DFT, and instead of telling the students how to run quantum espresso, I asked them to just try it. Describe the DFT task as accurately as you can, and use the input files. They could all run quantum espresso with minimal instruction. And this is important. You're delegating, when you use AI, you delegate power, right? When you set a mousetrap, you delegate power, right? That mousetrap is going to go off if someone touches. You're not making the decision. The mousetrap is making the decision. Even if your kid or your cat goes there, it's going to not know. So you delegate some decisions, but you don't delegate everything, okay? This is very important. Domain expertise is important. You need to verify and validate the simulation, just like with any other simulation that you run, any other code that you run. That still rests on the human. But this can make your life a lot easier. And by the way, today, actually, we have an LLM workshop on NanoHub we have a workshop coming up in a week where one of my students is going to discuss this work. If you take a picture to the QR code, you can sign up and participate in the workshop, and it's going to be hands-on. It's going to show you some of the tools and what we've been learning in terms of running simulations, if you want to snap a picture. So what do we need for AI? We need data, okay? And we're really bad at data, okay? So let me ask you, where's your data? Your experimental computation, where's all your data? Where? In your laptop? Yeah, okay. So that's what it is, okay? So our data, we generate data. It's expensive data. You spend a lot of time generating that data. The majority of that data ends up in local computing resources, whether it's at university. I didn't mean to pick at you, but we all do this, in a national lab or in a company. Now, when we publish, I'll pick someone else. Do you publish all your data? What data do you publish? The better ones, right? So this is also very common. You know, and this is not unethical or anything. You should show your best results. So the data that we end up publishing is biased, okay? A lot of negative results are never published, and that's bad for everyone, particularly bad for AI. And then when we publish, and this is all our stuff, what we publish is not machine actionable, okay? And these large language models are getting very good at extracting data out of publications, but they're not perfect. So it's kind of silly that the product of our work is then, you know, put in prison in a PDF, okay? So none of this is machine learning ready. Even if you share stuff on GitHub, as you probably all know, downloading something from GitHub doesn't mean you'll be able to run it in the next week or the next month or the next 6 months, okay? And so we need to make things fair, findable, interoperable, accessible, and reusable. And I know I'm okay. So I thought a little bit about, been thinking about how we share data, okay? And what we do as researchers is we publish papers, okay? And when you think about this, we more or less publish the same number of papers in the world as the number of songs published every year, 5 million songs, 5 million papers. So I went back and I found the first paper. It's widely recognized that the first paper that was ever published was in 1666 in the Philosophical Transactions in England, okay? And you can download the paper and read what they were saying. And if you think back then, to listen to music, you would either have to be friends with an earl or a king, right? Or someone in town played the fiddle and you could listen to music. All right, fast forward 200 years, we had the phonograph, right? So you could listen to music at home and you could buy records. And this is a paper from the 1850s. A little later, 1900s, the American Physical Society started publishing the Physical Review. Okay, you all know Physical Review? Wait, you know, back then there was only one. It's called the Physical Review. No B letters, no. We had the radio there, right? So you could listen to music, listen to the news, very different. I'm old enough that I remember cassette tapes, okay? And this is a paper from some of my friends in 1980. And now we all probably use something like Spotify or something like that. And that's a paper, okay? The only thing that changed is that we have a little color in the title, okay? That's the only thing that has evolved from 1666, okay? So I think we need to rethink how we share the product of our research. The product of our research is not that embellished description of your work. What's useful are the processes that you develop, the data that you generate and the understanding, the knowledge that you generate. So how can we do better? So I think it's important to, there's a big push to make data fair, findable, accessible, interoperable. So it's useful to others, okay? I think we need to make not just the data, but the workflows that generate data fair, okay? So it's not just the raw data or the pre-processed data, it's how you go if you're an experimentalist from the raw data to something you actually publish, a number, right? You never measure what you end up publishing. That analysis is not trivial. And different labs do it differently. Different individuals within the same lab do it differently. And that leads to a lot of noise in the published data. In simulations, in my field, the same thing. We set up inputs, we go through a complicated process, different labs do it differently. And there's no reason why we wouldn't share exactly the whole process, okay? My students work, they create folders by hand, the same way I did it when I was a grad student. MK there, run 1, run 2, new run. Yes, everyone uses the same. What's the meaning of new run? Or new, okay? And we all do this, and it's ridiculous, okay? And so what we want to do is take these. This is my publication, right? This is the output of the work that we did, where we refine the whole thing, how to do this simulation. Once I learn it, and I'm going to publish with it, there's no reason why I wouldn't make that a publication. Okay, so in NanoHub, you can actually publish these workflows. Any workflows that has inputs, does something, and has an output, you can publish it. All you have to do is use Jupyter notebooks to write your workflow. You have to declare the inputs. You have to declare the output. So we know what the inputs are and what the outputs are. You can add metadata. What do they mean? What it does, what it doesn't do. And then you publish it. When you publish it, you get a DOI. These are actual publications. They're indexed by Web of Science. Okay, so you can put it in your resume. I have them in my resume. And they're also queryable. So you can actually, with an API, say, is there a tool that can predict the bandwidth or can predict some kind of spectrum? And the tool actually knows its services, what it can give you, and what the inputs are, okay, what the requirements are. We also containerize it. Okay, so when you publish the tool, we put it in a container, and that tool will run forever as long as we can maintain that software and it's safe and not too old. But we have 20-year-old tools that run today just like they ran before, because all the libraries, all the environment, everything is containerized. So it's actually reproducible and people can then run it. So I'll give you an example. 2 of my PhD students wrote this very complicated script that does uses molecular dynamics to calculate the melting temperature of a high entropy alloy. It's not a particularly hard workflow, but it has a lot of analysis, okay? And you have to see it's a coexistence method, so you have to make sure you have liquid and you have solid and you're in equilibrium, and then you can say, okay, this is the melting temperature. So instead of doing this by hand like we always do, we coded all this into one workflow and we published it. And then I have an undergrad student who was interested in AI. So he took this loop of active learning, called the simulation as a service. He didn't have to see a single line of code of that simulation, just know what it did, and that it was developed by experts and tested and optimized. He found the alloy with the highest melting temperature in very few simulations, okay? Importantly, every time this is a published tool, all of you can run it. Every time anyone runs the tool, we store the results. So when he finished running this optimization, all the data was already in a database that we call the results database and findable. So by the time the referees looked at the paper, all the data was already there, okay? And now we have about 400 alloys that people have run through the simulation, and they're all right there. So I have another student that is, just to demonstrate the power of this, is learning from all of these 400 simulations, and now instead of 15 tries, it takes 2, right? And he doesn't have to call the other student and say, where did you leave the files? You know, what's the meaning of this? All of that is done automatic. And this is, I think, where we need to go. Just like Spotify. You don't think what the format is or where it's stored. You don't know. It doesn't matter where it's at, as long as you have access to it. I'm not going to tell you about this, just to say, except to say that you can use these, we call them sim tools, to ingest and analyze experimental data. So we have sim tools like that. If you collect experimental data, you have ways of analyzing, extracting peaks, whatever, you can publish it, and then your community can use your tool. And every time you use your tool, the data is stored and it's made available. All of this, I'm finished with this, I promise. I'll be saying that I'm finishing, and I haven't. All of these large language models, they're gigantic, okay? Meta, Microsoft, and Google invested $30 billion in hardware alone, okay? That's 3 times the NSF budget. But that's not all that's interesting, okay? So GPT-4 has 1 trillion parameters, 1 trillion. That's about 1% of your brain. Think how big that is, okay? But there's interesting things for smaller models in our field. So we've been working on something called parsimonious neural networks. And the idea is that you've probably heard this from Einstein. It's attributed to Einstein that the science should be as simple as possible. Occam's razor, as simple as possible, not any simpler. And so with these parsimonious neural networks, what we do is try to strike a balance between accuracy and simplicity. So for every neural network, we have a score of how parsimonious it is. And that has to do with how many adjustable parameters it has. We have custom activation functions, as opposed to using ReLU and functions that don't appear in physics. We use regular functions like linear, quadratic, and exponential. And we also penalize functions that are highly nonlinear versus linear functions. We can turn off and on neurons, and we use a evolutionary optimization, a genetic algorithm to evolve a population of models. Does that make sense? Some of the models are very complex, some of the models are very simple, and this parameter P strikes the balance between accuracy and simplicity. So we can actually generate a Pareto front of models that are optimal in terms of simplicity and accuracy. So these are models that try to predict the melting temperature of materials, starting from basic properties like elastic constants and lattice parameter, density, things like that. So the first model, the simplest model that we found, makes the prediction of the melting temperature proportional to the shear modulus, okay? And this is very well known. It's called the Cauchy instability, right? If you lose shear stability, you become a liquid. So that's the simplest model it finds. It's very physically intuitive. And then it corrects it. I'm sorry, the first one is with the Debye temperature. So theta naught is Debye temperature. Has to do with vibrations. Then it corrects it with shear modulus. And then it comes up with this expression, this red dot here. This is a very famous expression from 1904. It's called the Lindemann melting law. So Lindemann, from physics, from intuition, came up with this expression for when melting should occur. Okay? And the model actually finds it. And it's not at the Pareto front, okay? Which is very cool. These are tiny models, but it's very powerful. to finish, we also discovered if you do molecular dynamics, there's a very famous algorithm called the Verlet algorithm that's symplectic and it's time reversible. If you take a neural network and try to predict F equals ma, it's terrible because it doesn't know that it needs to conserve energy, that the time, it doesn't know time reversibility. If you force it to find the simplest possible expression, there's in the Pareto front, there's an algorithm that's way out there, and it's the Verlet algorithm. Okay, so when we started working on this, I thought, well, maybe we can beat Verlet. Well, we couldn't, but we found Verlet from data. It's very cool. You know, Verlet is something that people have developed. Newton started playing with Verlet all centuries of understanding how it works. You can find it directly out of it. And with that, I'll stop. This is my research group. These are the folks that help. We run NanoHub, and thank you very much.
Awesome talk. Questions?
Yeah.
Thank you for your great talk. In your talk about pan polymer experiments, you said rural resin has higher diffusion coefficient due to the void. Explain it again why.
Yeah. So what I said is that the glass transition temperature was lower. So if you imagine having a very ordered structure where all the chains are elongated and they pack very closely, and we know that these ordered structures, there's hexagonal packing in plane. Those chains are very tightly packed. So their mobility tends to be low. Okay, so imagine you have a glass with this ordered region and you're heating it up. You have to heat it to higher temperatures, right? To go through the glass transition, and then now the chains can move, right? That's what the glass transition basically means. Now, because of these voids, the chains are packed closely together, but a lot of the chains are near a free surface because you have these nanovoids. So a lot of these ordered chains have neighbors on one side and nothing on the other. So they're very mobile. They're very free to move around and relax. And so the relaxation timescales are much higher. They're much freer to move and relax.
And don't they have different scaling law for MST, for example? In MRPlus, like T over the number two scaling law is visible for the
Yes, so we don't measure MST because the timescales are too long for us. What we measure is torsional, the backbone, torsional relaxation dynamics. So we figure out how often a backbone torsion flips and the rate at which they flip. And so that correlates with, this is the alpha relaxation polymers. So when that relaxation starts happening at a high rate, that's where you've gone over the glass transition temperature. The glass transition temperature correlates with that alpha relaxation going to nothing as you're turning into a glass.
Following question. So in this case, it means that the number density of the older one will be lower than the models one.
I think so. Yes, that's what our models indicate, and I don't know that that's. Yes, and I know experimentally that there's porosity. Yes. So the answer is yes.
Other questions?
robots. Are there any efforts to, let's say, incorporate these sort of, let's say, automated
Efforts to, sorry,
what?
efforts to,
basically integrate these, let's say, automated data generation or high throughput platforms to
Yes, so we're working with a few, we're looking for collaborators. We're working with a few folks at Purdue there's a roll-to-roll experimental facility. We're trying to stream their data to NanoHub. That's one example. But this is relatively new, this symptoms and results database, and we're collaborating with other people that do oxidation experiments. I was showing an example. So we're looking for friendly collaborators. So you're all invited to reach out, and if you have questions, send me an email.
About the acid. For example, if you mentioned then the like physics or the internet, and stuff, but like how like did you need to like choose specific activation function?
No. So, well, no. So we have a bunch of activation functions. Of course, we know in the particular cases that I was discussing, we kind of knew what were the possibilities, right, what existed. So the network needs to be big enough to accommodate that expression. We have a series of functions or these are all custom neural networks. So what we have is each neuron has every neuron can have one of many activation functions. And when we do the genetic algorithm, you know that there's crossovers and random mutations. So a mutation would mean you take this activation function and you turn it from a linear function to an exponential function, or from exponential to quadratic. We have a list of functions. And then for every weight, that weight can be 0. So you can turn off neurons and make the thing smaller. The weight can be a fixed number, not adjustable. And we have a family of numbers because in physical expressions, like 1 appears all the time, 1/2, 2. So we came up with a list of numbers, and you can put that number and you don't touch it. It's not adjustable, or an adjustable weight. And the parsimony increases. 0 is the better one, fixed number, not adjustable is next. And if it's an adjustable number, it's the most complex expression. And we do the same thing with functions, from linear to nonlinear. And that's how we measure the complexity of the network.
Other questions? I'll take my privilege to ask the last question. If you were to evolve the publishing field today, what would you do?
I think the two things. First of all, the journals need to get better at forcing the data to be in a fair repository, okay? The funding agencies have, I don't know if you know this, but most funding agencies have a data share mandate, and actually there's not funding agency, but from the federal government that we're all going to have to share our data. But the problem is you can make a tarball of all your results, put it on your website, and then the data is available. And that's really doesn't help anyone. Okay, so I think we need to move into requiring fair data. That doesn't mean you have to use NanoHub, as long as a lot of these are interoperable, right? So I don't care if the data is on NanoHub somewhere else, but if it's on Figshare, and you cannot query Figshare, right? You need to go there and download the data. It's a table, CSV, and then you have to open it. And that's not, it's better than not sharing, that's for sure, but it's not the solution. And so that's one thing. I would encourage that. And the other thing is for the community. One of the challenges is that, at least in academia, we tend to be evaluated by the papers that we publish, the citations of those papers, and something called the H-index that no one likes, but everyone looks, okay? And it's there. And so I don't like it either. We need to have something that measures the impact of the data and the codes that you generate. So if you generate data and you make the data available, and that data is used to train a model, and that model saves a life, cures cancer, you deserve some of the credit. The vaccines, the COVID vaccines were developed in record time, and they even put a chip in it. I was joking. They didn't put a chip. But they were developed in record time because we have the protein data bank, in part because we have the protein data bank. Okay, and so the folks that students like yourself that did the measurements, right, and led to the structures that then are queried and then contribute to saving millions of lives need to be recognized, right? And I'd like to, if I'm one of those contributors, be able to put it in my resume. I contributed to that. And we don't do a very good job at keeping track of that. Okay, the impact. I think our impact in academia is very much focused on the publications, which I think is not in most fields not the most important outcome of our work.
Very good. All right. Well, let's thank Professor Strachan for an awesome talk.
Thank you all.